So if you go to my GitHub repository and you pull the latest assignment, you should be able to see what we're looking at here. This is programming assignment number 5. And what this is going to be is a way to talk about or how to apply various design patterns from the so-called Gang of Four book, which we'll be covering in the course. And it'll be used in the context of a gravitational simulation program. So you get a chance to use patterns like iterator, which we've done already, visitor, factory method, singleton, and composite, and also prototype. And it'll also give you experience with other STL algorithms such as transform, fill, and copy-n, as well as other ones that you may choose to implement as far as improving and updating your array list implementation from the previous 2 assignments. There's a bunch of header files and CPP files provided here that will give you a starting point. You'll have to have at least a bit of understanding of a few basic principles from physics to understand the simulation, and I'll go over those in a second. Don't worry if you're not a physics major or you haven't taken a lot of physics. The Vector 2 class, which you have to fill in bits and pieces of, provides the bulk of the math that you'll need to do this. And I provided a lot of the hard stuff for you, so you'll just have to work on some things involving the use of STL algorithms and so on. As always, don't change the header files unless you see something glaringly wrong, in which case, please come talk to me. Start early, ask questions. This assignment is going to be cumulative, so it'll expect that you have everything working properly from assignment 3 and 4 in order to be able to do assignment number 5. One of the tests here simulates every second of the Earth and its journey around the sun for a year. So when you run the test, it may take a little while to execute. It probably takes about a minute on my computer. So I'm not sure whether you have a computer like mine, but it may take a little bit of time to run. So here are the classes that we're going to focus on. I'm going to give you an overview of them here, and then we're going to go look at the skeletons to give you more insight as to what you need to do. There's a class called Universe, and it's responsible for keeping track of all the objects that are part of the simulation. And the universe, there's only one universe, so we're going to make this a singleton, or you're going to make this a singleton, implementing the singleton pattern. And we'll talk more about where you can find these various patterns, find information about these various patterns shortly. We will, of course, cover these patterns in the class, but if you want a head start, you may want to go to my website, and you go here, you'll see that I have a playlist called Pattern-Oriented Software Architectures for Concurrent and Network Software. And this was done a number of years ago. And there's a lot of videos here, all of which are interesting, but many of which are not relevant for the discussion we're about to have. If you go towards the end, the last dozen or so videos here, if you go all the way to the end, you'll see that at some point I start wearing this kind of maroon shirt, and it says Appendix, Introduction to the Case Study of Gang of Four Patterns. We will, of course, cover this material in this class in the remaining sessions. But if you want to get a head start on some of the patterns, you might want to watch videos, for example, on iterator, visitor, and prototype patterns. Those are important for our purposes here because they're relevant to the assignment. And then there's also a video about factory method and abstract factory that could be interesting and useful. There's a video here about the singleton pattern that you might want to take a look at. And then there's also a video about the composite and bridge patterns. So if you want a head start, go ahead and watch these videos. They cover a lot of the same stuff that we'll cover. They're just done in a slightly different fashion. And but the case study example is the same, just a little different here and there. But if you need a head start to catch up on what these patterns are, take a look at those videos. I also recommend that you go and read the corresponding material in the Gang of Four book, which you should have access to as the primary textbook for the course. So continuing on with the discussion of the classes that we have, there's also a class called Object, and that's the base class of a class hierarchy that's designed to provide the interface for the objects that are used in the simulation. And certain objects may be composed of other objects. So this class should be capable of being used to implement the composite pattern. Correct handling of the different types of objects of this class provide an access point for a visitor using the visitor pattern. So when we talk about the visitor pattern, you'll see there's a method called accept that is expected to be part of objects that are going to be visited. And so there's an accept method here. And there should also be a snapshot method, or you should implement a snapshot method that is available using the prototype pattern. There's also a class called Object Factory, which is an implementation of the factory method pattern, and that provides a convenient way of creating the appropriate type of objects based on a string argument that's passed to it. There's a visitor abstract base class, as well as a concrete class called print visitor that's used to test the visitor iterator framework that is done as part of the testing suite that you have to be able to pass. And then there's also a class called vector2, and that represents a two-dimensional vector of doubles. And this is not STL vector. This is a mathematical concept of vector. It's a two-dimensional mathematical vector. We'll look at that in a second. And all the implementations of the methods there should be done in a loop-free manner. So you should use no for loops whatsoever. No for loops were harmed in the making of this class. You can imagine a disclaimer like that. And instead, you should be using STL algorithms in conjunction with functors and or lambda functions. So a lot of the code for vector2 is provided for you, but you'll have to implement some of the methods to demonstrate your mastery of STL algorithms like transform and fill and copy n and so on. There's a number of physics concepts that you need to be familiar with to do this assignment. Again, you don't have to be an expert at physics to make this work, but there's the law of universal gravitation, there's the second law of motion, there's the net force acting upon an object is equal to the sum of the forces acting on it, there's the acceleration of an object, which equals the change in its velocity divided by the corresponding change in time. There's the velocity of an object equals the change in its position divided by the corresponding change in time, and so on and so forth. And all these concepts of acceleration and force and position and velocity are all implemented in the vector2 class. Again, you'll have to fill in the blanks on some of those things, but the bulk of the hardcore physics-oriented math is provided there for you. You just have to focus on using the STL algorithms to do some of the computations. And we'll talk about that in a second. So when you do this implementation, take a look at the tests. We'll look at them shortly. There's a test called the UMC test, which includes a loop that goes through the entire year with a step size of 1 second. And it uses state information for each object in the universe to calculate the state for the next step. So make sure that you look at that. I think, again, a lot of that code is provided for you, but you should understand what it's doing to understand how the other pieces have to work. I recommend you start with the 2 easy tests first, which are called inertia and visitor. And once these are working, then you can move on to make sure the UMC test works. Don't change any of the CMake related build files unless something really weird is happening, in which case, of course, please contact me. You'll be focusing primarily on making changes to the .cpp files in the source directory. I have provided the solution to most of the vector2 class. You just have to fill in the various parts marked to do, you fill in here. And we'll look at that when we look at the code in a second. Make sure that your array list and iterator and scoped array classes from the previous assignments are working, because you're going to need them for this assignment. You'll also have to implement const iterator for array list. Some of you have done this for assignment number 4, in which case, great job. I think you probably realized it wasn't very hard to do once you had array list iterator working, and it greatly simplifies some of the code in the array list implementation itself. This will also, of course, give you further experience with the iterator pattern. So this assignment is not only showing how to use more advanced STL features we've been talking about, but it's also giving you a chance to apply a bunch of patterns. And everything else is the same as always. Indicate you're aware of the honor code. You have to do it yourself. Don't make changes. Follow the coding conventions, and so on and so forth. Okay, so that's kind of an overview of the assignment. Let's now go ahead and take a look at the include files. So you can see you have to bring in your array list and array list iterator implementation from before. I provided you with header files for these, so we'll focus on the .cpp files. Then there's these object files and parser and other kind of stuff we'll look at in a second. There's a corresponding set of source code files for everything. For these, I gave you kind of the rough skeletons for array list and array list iter, and go ahead and copy and paste in your implementations into these skeletons. This just makes sure that everything in here has the right signatures we expect. So be a little careful when you integrate your code, but it should be obvious where everything goes because it's basically more or less cut and paste from your previous assignment, plus the fact that you also have to implement the const iterator as well. And I'll be giving you feedback on your assignment number 4 solution later today. I took a look at a couple of submissions this morning, and the ones I looked at were really good, so that's great. I think some people seem to be realizing that once you get the iterators working, a lot of the other implementation code gets really simple and really clean and concise. So once you have that epiphany, I assure you, your life will be much easier when you write that code because it's very, 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 very parsimonious, to use a fancy word. So array list, iterator, and scoped array, these are all things you'll have to provide from your previous solution. Now let's go ahead and start taking a look at the other parts. So let's start with vector 2. So vector 2 is a two-dimensional vector of doubles. This is not a vector in the STL vector sense. It's a vector in the mathematical sense of a set of points that go in a particular direction. And based on various computations, you can figure out things like acceleration and velocity and all this good stuff. You're not to use any for loops or while loops or do while loops in this implementation. You should only be using STL algorithms in conjunction with functors and iterators and lambda expressions and so on. This also allocates the memory statically, so there's no need to have various other operations like a destructor, a copy constructor, an assignment operator. Those are not needed because the default ones that come out of the box work perfectly fine. Down here, we have a bunch of methods. There's a default constructor that kind of zeroes everything out. We have a constructor that's a copy constructor that just does the member-wise copy, which is built in by default. There's something that takes an array of doubles and it copies the first 2 values because it's a two-dimensional vector into this vector 2. And there's an assignment operator that uses the default as well. And of course, we don't have to worry about the move semantics because number 1, it's very short. And number 2, we're not allocating any memory dynamically. We then have a bunch of operations that do various things based on the contents of a vector 2. For example, if you give it another vector, it'll add the vector that we have with the right-hand side that's passed to it and then give back a new vector. There's a way to do scaling. There's a way to compute the inner product or the dot product of this vector. If you ever have any questions about that, just Google inner product and you'll see how it works. It's very simple. I give you some of the implementations here. There's a square root of the magnitude of the vector. There's the magnitude of the vector. There's a normalization method. There's one that converts it to string. And then we have a bunch of overloaded operators that do various things like return the additive inverse of the vector, return the difference between a vector and a parameter, return the sum, check to see if the vectors are equal, check to see if the vectors are different. There's subscript operations. There's plus equal, divide, times, and so on and so forth. So some of these methods you have to implement. Some of them are provided for you. There's also some private iterator methods that you can use in the implementation in order to simplify the way it works and avoid the need for any looping. So you can use the iterator mechanisms here in conjunction with the mechanisms that come along for the ride with C++ and the STL algorithms. And then the implementation of this is just a two-dimensional array. All right, so let's go ahead and take a look at the implementation class for this. Again, some things I provided for you, some things you have to do. So you have to implement the initialization by using fill in conjunction with the iterators. You have to implement this thing that takes an array of doubles and then copies the first 2 elements using copy_n. Here's the add method where you have to sum this vector on the right-hand side. And the way you're going to do this is by using basically transform in conjunction with functors and so on. So you'll have to use the transform algorithm to do this. There's also a method here that you use in order to do scaling. And so you'll scale a copy, and if you take a look, you can see how to do scaling. And once again, you'll you'll use the transform algorithm. And then there's also one here that does dot product, which is the inner product. Again, take a look at that. And you have to use the transform algorithm for that. So these are basically just giving you experience writing algorithms using transform. I provide you with a bunch of implementations. There's the square root, norm square root, there's norm, there's normalize. I provide all that stuff. Here is the equality operation, which I provided for you, which basically checks to see whether things are within epsilon using the equal operation. Here's the not equal operator. Obviously, subscript is just indexing into the array. And then we've got a bunch of other operations that do various things that use the pieces that you implement. So if you implement those things correctly, all this math will be correct. And then down here, we've got the various mechanisms that are working on the iterators. Should be, shockingly easy to do. Once you think about what's going on to implement iterators, you don't have very much to have to think about. It's really simple. And then this just allows you to be able to do commutative operations for multiplication. So that's vector 2. The main thing in vector 2 is to implement the iterators and then to go ahead and also implement the various methods that I have to do designated at. So take a look at that. And I think if you look at your C line, wherever something is a to do, it's actually marked as a light blue line. Now, by the way, this code will not compile out of the box until you add all those features in there. So don't be dismayed if you see red bars. You just have to add the code in to do the right thing. Okay, so that's the vector 2 implementation, and that's kind of the heart of the math that underlies the simulation. Let's talk about some of the other methods and classes here. Here's the object class. This is the mechanism that's used to keep track of objects that are suitable for use in the simulation. And you can see here that it's got a bunch of virtual methods. It's got an accept method, and it's got a clone method, which is used for the prototype pattern. This is used for the visitor pattern. It's got a bunch of other methods that return characteristics about the object. These are, of course, celestial objects like the sun and the moon and so on, and the earth. And then it has other things about the position, the velocity, the force, and so on and so forth. A lot of this stuff is used by the test program to do various things. And then here are the actual elements: name, mass, position, velocity. You can see those are vector 2s. If you look at the class down here, you have to implement the accept method using the mechanisms we'll describe in the visitor pattern. So we'll, of course, cover that in class, but also feel free to go watch the video I gave you a pointer to a minute ago. You have to implement the clone method. Go ahead and watch the video about the prototype pattern to see how to do that. And then I provide you with a bunch of the other stuff. And most of these things just return the underlying data members. Here's the get force method that figures out the force. I give you the math for that. You also have to implement operator equality and operator inequality. And remember to do operator inequality in terms of operator equality. So compare things using equality and then negate it. And you'll have to put the comparison inside of parens to make the precedence work correctly. So that's what an object is. Well, that then leads to the question, how do you create objects? And you create objects using an object factory. Surprise, surprise. And we have a method here called make object, where you pass in the name of the object and its mass and its position and its velocity. So these are all part of simulating the world, or the universe rather. And you can see this is a static method. So we could make it static or non-static. It could go either way. In this particular case, it's static, but we could have done it a different way. We'll talk about that when we talk about the factor method pattern. And then over here, you can see that you have to implement the make object factory method. Now, there's different ways to do this. If you want to do this as the composite pattern, you can do it that way. If you just want to implement it by creating an instance of object with the appropriate fields passed in, you can do it that way. But the goal is to sort of understand what a factory is. And in a nutshell, a factory is a pattern that allows you to decouple the creation of something from its use. And sometimes creation is kind of messy, but use is very simple. And that's certainly the case with this example. Once you have an object, it's been initialized, it's easy to use. So that's what the object factory is. There's a parser, which I give you, which basically loads in files that are used for various purposes to drive the simulation. Since you are given that code, we can not worry about that too much. Let's go take a look at universe. That's an interesting class. So the universe is a singleton, which is the singleton pattern, which you'll learn about. And it represents the series of objects, the celestial objects that represent the universe in our program. For this assignment, the first object will be the sun, and it'll be unmovable. So at least from one point of view, the sun never moves. Everything revolves around the sun. This isn't a Ptolemaic worldview where the sun revolves around the earth. So the earth and other bodies, other objects, revolve around the sun. You can see here that we're going to use our array list implementation from assignments 3 and 4. So make sure that that's working. And we're going to have the array list holding object pointers. So not objects themselves, but pointers to objects that we allocate dynamically. And again, there are lots of different ways we could do this. Here is the instance method. When you read about the singleton, you'll see that you have to have a method called instance that returns the one and only instance. I should say the one and only instance of the universe. So there's only one universe, at least in our cosmology, there's only one universe. And then we have some methods that return iterators to the underlying universe objects, and that should be very straightforward to implement, of course. And as you can see here, I probably should also mark these as no discard as well. Let's see, this probably is wanting me to mark this as no discard. Let's see if it's saying that. Yep, that's what it's saying. So there's also a method called getSnapshot, which uses the prototype pattern, and it goes ahead and basically makes a snapshot of the current state of the universe, and that's used for steps in the simulation. You can set the simulation, you can swap things. So this is good old swap. You've been working on that to do exception-safe management of data objects. The constructor is private because you only want to allow creation of universes from the instance method, so there's just one of them. And then we have some other methods that are used to add an object to the universe and to release the array of objects that we're getting rid of. And then we have our array list of objects, which are the registered objects that are registered by add object. And finally, we have a static pointer that ensures there's only one of these things. So once you understand the singleton pattern, this becomes a lot more clear. Notice how we're also a friend of Object Factory. So, or rather, we're letting Object Factory be a friend of ours. And that means that Object Factory can access methods like add object and use that as it needs it. Okay, so that's the header file for universe. Let's go take a look at the implementation. We start out with a static inst data member being null. You have to implement the instance method using the singleton pattern, so go ahead and look at that, how that works. The destructor will go ahead and clean everything up by freeing all the elements. Add object goes ahead and adds an object into the underlying array list of objects. Begin basically goes ahead and gets an iterator to the beginning of our universe. That should be pretty straightforward to implement once you have your iterators working. So we have non-const and const iterators, so you have to make sure your const and non-const iterators for array list are working properly. GetSnapshot is going to go ahead and, this is a very interesting method. It's going to iterate through the array of objects, and it's going to clone each object into the corresponding element. And to do this, you'll have to understand the prototype pattern. And it's also fun to see how you can write this code using only STL algorithms. So again, you should try to avoid using loops. I sat down last night and cranked out a very clever version that uses the for each algorithm to good effect. And it was very clever. So see if you can try to get around it without using loops. You should try to have loop-free implementations wherever possible. Here was the simulation model. this was somewhat convoluted, so I didn't go to the trouble of trying to remove loops, although I probably could if I really put my mind to it. You don't have to write this code, though, so don't worry about it. Down here, you will have to write the swap code, which is going to swap the contents of the array list that's provided here with the existing array list, and then it'll release the old version. And release, of course, is down here. And that will go ahead and call delete on each pointer in the list, because remember, it's an array list of pointers to objects. So we have to delete each of them. And then we go ahead and clear the container, which deletes the item. It deletes the underlying array list altogether. So you'll have to make sure you get that code working. It's not too hard. It just requires you to think about the methods that you've got and how you would use them. Okay, the last piece of the puzzle here is the visitor class. This is used to implement the visitor pattern, and we use this basically to be able to print out all the elements in our simulation. And in this particular case, we're kind of doing a stripped down version of visitor. So it's not showing visitor in all of its full glory, as we'll talk about in the slides. But it's a good starting point to get you accustomed to the concept of providing an operation that's decoupled from whatever it is you're iterating over. And so we have a visitor base class, which has a visit method that's a pure virtual method, which means it has to be subclassed and overridden. And it's passed in a reference to an object, which of course will be an entity in our universe. And then we make a print visitor, and the print visitor will go ahead and visit this and print things out. And as you'll see here, we'll look at kind of the structure of this in a second. When you create a print visitor, you also give it an OStream, and this OStream is used to print the contents through the visit method. So let's go look at the visitor class itself. There's just a handful of methods that you have to do here, and that's what they are. So let's see if we, whoops. So you'll have to go ahead and implement that method. Let's see if I can. All right. So you're going to have to go ahead and do this correctly. It's complaining at me right now because I removed some code. And then you're going to have to implement the method that visits the object and prints out its contents. So again, take a look at the visitor video or wait until we cover that, which will probably be Monday or so of next week. Okay, so that's an overview of the skeletons. Now let's go ahead and take a quick look at the tests. So as you can see, there's a bunch of tests here where we create a universe and we grab our universe singleton and we stuff it away into a unique pointer so we can delete it and free it up later. We use our factory method to make the sun, which is the big kahuna that everything else revolves around, literally. Then we go ahead and make our two-dimensional vector, and then we make some other objects. And in this case, we go ahead and do some simple simulation tests to run for 50 time steps and do operations on the universe to iterate through it. You can see we're iterating through every element in our simulation and checking to make sure things are correct and so on. So that's the inertia test. Then there's also the visitor test, and visitor test is used to go ahead and check whether our visitor is working correctly. And this is mostly just seeing if it works. So we're going to make a bunch of objects that just print out hello, not particularly celestial, if you will. We create ourselves a universe, put a bunch of objects into it, and then we make ourselves a print visitor. We iterate through from beginning to the end of our universe, and we accept the print visitor into every object that we've created. And that will, of course, go ahead and print out the contents. And what we expect when we're all done is we've got ourselves a stream that says hello, because that's the objects that we created. And then the final test, this is the one that does more of the physics-y kinds of things. This goes ahead and will test the uniform circular motion path. That's what UMC stands for. We open up a file. This is all code that you're given. We open up a file that tells us information about the entities that we're creating. We go ahead and make our sun. We make the earth. We make ourselves a year in seconds. It's a lot of seconds in a year, of course. And then we kind of go through this whole thing a chunk at a time and run the simulation. And this test will actually take a while to run. probably a minute or two or so on your machine. Depends how fast it is and how much memory you've got. But I think that'll give you good ways of exercising all the different features that we're doing. And it'll also give you a chance to improve upon your knowledge of STL and improve upon your knowledge of patterns. Okay, so that's basically everything there. As you can see, there's a lot of moving parts. The good news is you don't have to understand and implement all the moving parts, but what you do have to do is understand how they all fit together, understand what the patterns are, and then understand how to implement the STL algorithms that we've talked about.